Okay, let's start. Until last week, we were talking about what is the regulation and what is the classification. Okay, okay, let's go back to the lecture two. In the lecture two, we were talking about what is the supervised learning, what is the linear regression or the regression problem, right? Uh, there was the housing price expectation. With the size of the house, we can predict the price of house using the deep model, right? So to develop the machine learning algorithm, we need a training set of the housing price in historical manner. There, there should be the size of the house with the price of the house in a fair as a fair training set. And in the regression problem, we we train the model that predict output of the new input or to understand the effect of the input on the output. Okay, so for the regression, there is the input variable, output variable, right? And right. So we need a mapping function or the hypothesis or the just function of the linear regression. So in the linear regression, there exists just the linear equation, something like this. So in this case, W0 and W1 are parameters that we have to learn in during the training phase. Okay. So after determine our mapping function, we have to find this parameter W using some kinds of optimization technique, right? So before that, we have to we have to determine the cost function. So cost function means the distance between the estimated values with the ground truth values, right? Okay. So for example, if we have a training sample xn and yn is output of the yn is the output we want to estimate, then if we have the mapping function something like this, let's say the fw of x, then our cost function is going to be the estimated value and the ground truth value, and the cost function is going to be distance between the estimated and granted ground truth value, and we aggregate those distance using across the every samples in within the training data. Okay, so this is the cost function. By minimizing this cost function, we can find this w, the parameter of our machine learning algorithm, using some kinds of the optimization. In this course, we just talk about the gradient descent algorithm, but there are so many variants of the gradient descent algorithms. But we just talk about just the simple gradient descent algorithm, right? So yeah, there was some cost function intuition. So cost function can be represented using the contour plot like this, right? Right. So there is two kinds of the cost function that are popularly used. So yeah. So there is a gradient descent algorithm, right? So the idea is start from some initial parameter values and keep changing the parameter to reduce our cost function or loss function until we hopefully end up at the minimum. Okay, so this is the plot of the gradient descent, right? Right. And then in the third lecture, we were talking about the classification, right? Before classification, we were also talking about the multiple feature case in the linear regression problem, right? So we can extend our simple mapping function, something like this, right? Right. In this case, please be careful. This is not the square of the xn. It's just the second element in the xn features. Please see this table, okay? And so with this mapping function, it can be reformulated something like this as a vector multiplication form, right? And yeah, we can propose the new gradient descent algorithm for the multiple variable cases, right? So yeah, there is another solving method called the normal optimization or the normal optimization solver, like this. Yep, looking like that, like this. Yeah. Comparing to the gradient descent algorithm, normalization don't need to choose the learning rate and don't need to iterate, and but to compute this inverse of the matrix, we need the high computational complexity. So it will be really slow if n is really large, such as the n is equal to 100 or n is equal to 1000, something like that. So yeah, it was the summarization of the linear regression problem. And what was the classification? Classification is to relate the input variable x to the output variable y, but in this case, y is the discrete variable, or in other words, the y is the categorical variable. For example, so in the final classification case, y should be lie in 0 or 1. So 0 means the negative class, the 1 is equal 1 means the positive class, okay? So yeah, when we have a constraint to the mapping function such that the mapping function should be larger than 0 and lesser than 1, we call this mapping function, we call this problem using this mapping function is the logistic regression or the classification, okay? So please be careful. Logistic regression is the different to the linear regression problem, okay? So there is the difference, logistic and linear, okay? So for the logistic regression model, we need some kinds of nonlinear mapping function like the FG. FG looks like this, okay? So the property of this mapping function is like this, so it lies in this constraint. So with this nonlinear mapping function, so we can represent the mapping function of the classification problem, something like this. So we just call this function as a sigmoid function or the logistic function, something like that. So the output of this mapping function is going to be probability that y is equal to 1 given input x with a parameterized by the parameter w, okay? So this is the logistic regression problem, and so the logistic regression problem have the decision boundary. What was that? So as you can see here, if there is two kinds of the samples with two labels like this, the decision boundary is the straight line or straight the plane that separate those samples, something like that. The decision boundary can be the nonlinear values like this. Yeah. So the comparing to the linear regression, for the logistic regression, we need another cost function. For example, if we use the same cost function called the MSE like this, then used in the linear regression problem, the cost function shape of the cost function looks like this, right? Because the nonlinear term in the mapping function. So in this case, it is really hard to find the global or the local uh, reliable local minimum. So we need another cost function for the logistic regression problem or the classification problem. So we introduced the new cost function defined as follows. In case of yn is equal to 1, the cost function looks like this, and yn is equal to 0, the cost function looks like this. The property of this cost function was something like this, So it has a good desirable property that we want to do to solve the logistic regression problem or classification problem. Okay, so we can represent the cost function for logistic regression as a generalized form, something like this, right? So with this cost function, we can also using the gradient descent algorithm to find this learnable parameter W. Okay, something like that. Okay, so yeah, comparing to the previous one, we also talking about the multi-class classification using the one versus all method, right? Or one versus all technique. Comparing to the binary classification, multi-class classification, in multi-class classification, there's no single decision boundary. So what we want to do is use the one versus all technique such that we can divide this multi-class classification problem as a three sub-problem. In the first problem, we determined this one as a positive class and these samples as a negative class, and then find the decision boundary for this case, and we can do similar things on another case, something like this. So by using these three kinds of the mapping function, we can do the multi-class classification. Okay, like that. So finally, we were talking about what is the discriminative model and what is the generative model, right? So as you can see this figure, in the discriminative model, we try to find this decision boundary, right? So it is same as to model the probability of the output y given feature x, right? But in the generative model case, we want to model the distribution of the individual class, something like that. So in this case, it is same to model the joint probability of the input feature x and output y. So in other words, in the generative model, we try to learn the probability of the features given label y and the prior probability of the py, and then with these two probability we finally estimate this probability, the probability of the label y given x. This is exactly the same to this one, but comparing to the discriminative model, we cannot estimate this probability directly, but we try to estimate this one, and estimate this probability using those probability. something like this. So this is called the Bayesian rule. So yeah, it was the generative model. Okay. Okay, let's move on to the today's lecture, right? In today's lecture, we were talking about some kinds of the learning theory and some kinds of the l- um, some concept to stabilize our learning algorithm. Okay, let's start with underfitting and overfitting. Okay. Okay. Until today, we have talked about the machine learning model, such as the linear regression model or the logistic regression model, right? But okay, if we have the training sample and if we determine the model or the network or our machine, let's say machine or network, let's say network. I guess some of you already heard about the network, but that term of the network used in the deep learning stuff, right? Because the deep learning, in deep learning, the parameter are composed of some kinds of network. So we will discuss this one in our later course, but in this case, just say the parameter is the network. Okay. So we have a model machine or the network. There are several possibilities. The first possibility is the model can be too limited to model our training data, or they can be too rich to model our data. What does it mean? So here are definition. So there is the definition for underfitting problem. So underfitting means we can't find the function that is good fit for our training data in our model. So that is the kind of the underfitting problem. Okay, so here's the example. Okay, we have a 5 training sample, right? So it will be something like xn, comma yn. So xn is the size of the house and yn is the price of the house. So this is the same example in the previous lecture, right? So okay, in case of linear regression problem, we want to find the straight line that approximate those training sample well. So first of all, let's say using this mapping function, something like in this case it looks like this, right? So we determine to use this mapping function, and then we have a training set, and we can use some kind of optimization like the gradient descent to find this parameter, right? So something like this. Then in this case, this optimal parameter makes some straight line like this, right? Because this straight line will approximate those sample, something like this. So in this case, this is some kind of error with the estimated and the ground truth, right? So, but in this case, we can, this straight line is the optimal solution, but still there are some error here. So there is no way to reduce those kinds of error using the linear model, using only linear model. So this is the best possible solution using the linear model, right? But we want to reduce those error as much as possible, right? So in this case called the underfit problem, right? So underfit problem means that we cannot find a function that is a good fit for the data in our model because there are inherent error like here, right? So how can we solve this problem? How can we solve this problem? We can use the more high dimensional feature or the extended or augmented feature vector. Let's say comparing to this example, we can use the more higher dimensional features like the squared x x x power 3, something like that. So in this case, comparing to this line using this linear function, by using those kinds of mapping function, let's say we can find the more accurate mapping function, something like this, or using the more much higher dimensional mapping function, we can find the mapping function looks like this, something like that. Okay, let's read through that. We can find the mapping function like that, right? Okay, so comparing to this case that has some inherent error like this, by using the much higher dimensional features, we can reduce some error. In this case, there's no error comparing to this one, right? So okay, so in these two cases, the errors are getting reduced, but as you can see here, this model can model the training samples well, but it fails to generalize to a new sample. Or let's say if we have we had the training data set, but if we have the test data set, let's say, okay, what about the price of this site? Let's say new feature X. But in this case, this algorithm predict the price of this sample, like this, but it might not be the good solution. So it has limited generalization power. So in this case called the overfitting case, right? Okay, if we go back to the previous one. So what is overfitting? We had a rich model. We had a rich model family, something like this, right? That we just fit the underlying function, but we fit the noise in the data as well. What does it mean? If there is some kind of noise in the training data, something like that, so that mapping function run the training model, something like this. So it's not our desirable output, right? So in this case, this is the just the right case, right? Then okay, so when we decide to when we model our mapping function or our learning algorithm, there are several kinds of the possibility. So in this case, our mapping function maybe to underfitted or overfitted or the just right to the training data set, right? Then how can we determine the learning algorithms underfitted or overfitted? Okay. By the way, when we consider the logistic regression algorithm, there is also underfitting and overfitting problem. Okay, so for example, there is two kinds of the class, the X class and circle class, right? If we just use this one here, this is the sigmoid function, right? Because this is just a linear equation, so the decision boundary of this mapping function is looks like this, right? But there are still errors here, right? So in this case, it should be x, should be circle, but there are some kinds of error. So if we use the much higher dimensional one, we can find the more proper decision boundary like this. But still there are errors here. Then if we use the much higher dimensional boundary like this, we can find the solution, something like that. So in this case, this decision boundary separate those training samples well, but it has a limited power to generalize for the new samples or the testing data set. So we will discuss this one today, right? So actually the overfitting problem is the problem that we are suffering when we develop our our machine learning algorithm. So we want to find the mapping function, something like this, but in most cases our trained decision boundary looks like this, so it's not desirable property. So there are several kinds of the method to reduce this overfitting problem. Okay, so first thing we want to do is just use the more training data set. If we have a large scale data set, there may be some noise, but at the same time, the possibility of the good distribution of the training samples are increasing. So first thing we can do is to use the more training data set, right? So second thing we can do is to reduce the number of features, or just using the simpler model. Okay. So comparing to this one, this simpler model produced a better model. But if we just reduce our complexity of the model, something like this, there might be another problem called the underfit problem, right? Underfit, let's say this is overfit. So we have to choose carefully our training model. So that's why we need a model selection algorithm, which will be discussed in the later in this lecture. Okay, so this term or this statement means we have to choose the proper model for the training data. Okay. Another possible way is to use the regularization. So the regularization is the topic of the today's lecture. So what is the regularization? Simply, we want to keep all features, but we want to reduce the magnitude or values of the parameter. maybe you can't understand what this statement means, but we will discuss this the later. Okay, so in this now, just remember the regularization is keeping the feature but reducing the magnitude or values of the parameter. So it helps to reduce or the overcome the overfitting problem. Okay, so this regularization works well when we have a lot of feature, which each of which contribute a bit to predict y. Okay, let's see the detail in the next slide. So the first solution looks like this. Okay, so let's say n is equal to number of samples and m is the degree of the our model. Okay, so this is the degree 1, right? Because there is only a first order variable, right? So but in this case there are second order variable, right? So this is the degree 2, right? But in this case there are 3, 5, 4. So there are d is equal to n, and when n is larger than 2. Okay, so this is the degree of the polynomial function, right? So anyway, let's say this green is the ground truth mapping function that we want to solve, right? And there are some training set as a blue dot. So if we use the third order polynomial function to approximate this sample, the mapping function looks like this. Okay. But if we use the much higher dimensional mapping function, a higher dimensional degree, let's say the m is equal to 9, the shape of the mapping function looks like this. So as we discussed previously, this mapping function has the low error rate, right? Error rate, because the data fitted well comparing to this one, but this model is more similar to the ground truth one that we want to solve. So we could say the m is equals to 3 is the more proper model than m is equal to 9, right? But okay, let's say if we increase the n is equal to 15. So I mean n is the number of samples. So however, if we increase the number of samples, something like this, with the m is equal to 9, so this model can fit it well to the training samples here. So it is similar to the ground truth mapping function in a green color. So we can say that, so by using the more data set, we can train the more proper mapping function. Okay, so this is the first way to reduce the overfitting problem. By the way, there are very interesting paper related to the overfitting. Called a few useful things to know about the machine learning. So please see the section 3 and section 5 to understand what is overfitting and how can we overcome that. Okay, so I suggest you to read this paper. Okay, so the third thing, right? The third thing we can do to overcome the overfitting problem is the regularization method. So what is the regularization? Here's the intuition. Okay, Let's go back to the house pricing expectation. We have a training sample like this with the size of house and the price of house. So this is the input, this is the output, right? So if we use the mapping function, something like this is the second order polynomial, right? So in this case, the mapping function looks like this, right? This mapping function is similar to the ground truth. Actually, we don't know the ground truth yet, but we can say that this mapping, we could say that this mapping function approximate well the distribution of our samples, right? But if we consider much higher degree of the mapping function, something like this. In this case, this is the first order, what's that? First order polynomial mapping function. Let's say this equal to 4. The shape of this mapping function will be looks like this, right? So there is a overfitting problem, right? So why there happened the overfitting problem compared to this one? Because of this higher order term, right? Here and here. So what I want to do is to reduce the effect of these two terms to make our new mapping function looks like this, similar to this one, right? Then how can we do that? How can we reduce the effect of these two terms? Okay, there is the objective function of this linear regression problem, right? So this is the ground truth, okay, and this is the estimated value, and W was the parameter, right? So let's say in this case the theta is equal to W, right? Okay. What if we add this term like the W3 W3 square or 1000 times W4 square? And then if we just minimize this function, we can reduce. Okay, what makes this loss function as a 0? When W3 is equal to 0 and W4 is equal to 0 with this function. So in this case, using those kinds of terms, we can reduce the effect of this higher order term, right? So then by using this function, this kind of function, we can estimate the new mapping function larger than this one, even though we still use this higher dimensional or higher order polynomial function. Okay, so this is the idea of the regularization. So in other words, smaller values for the parameter, let's say something like this, then it can induce the simpler hypothesis or the simpler mapping function. Okay, so in other words, by using the high regularization, we can make this higher order polynomial function as a simpler one, right? Reducing this effect. Okay, so it is less prone to the overfitting problem. Okay, so comparing to the original optimization function, we add the new term, something like this. So what does it mean? So by minimizing this term, we can reduce the impact of this each parameter samples that related to the each features. Okay, so by using this term, we can reduce the effect of the redundant features or the higher dimensional features. Okay, higher order features. Okay. Okay. So let's see the example as well. So yeah, here. So okay, here is a new objective function that we want to solve. So if we just minimize this term, as similar to the previous our previous lecture, the shape of the mapping function will be looks like this. So the parameter w decide the shape of this mapping function, right? So this is called the overfitting, right? Then, however, if we serve the new objective function, something like this, with this term, the shape of the mapping function will be looks like this. This will be the new parameter set that approximate the distribution of the training sample well. Okay, so this is the role of the regularization. Okay, so here is the formal definition of the regularization. Okay, what is the regularization? Through the regularization, we can penalize the complex model or the complex features and favor simpler one. So what is the formal definition? Here is the objective function that we feel, let's say just L over W. W is the parameter, right? So comparing to the previous one, we add the new function of the W. So finally, this original loss function and new loss term are added, and we minimize the this overall loss function on the parameter W. Okay. Here, this second term, is called the regularizer, and which measures the complexity of the model given by W. Okay, so this is the formal definition of the regularization. In the previous example, we used the second order term in the regularizer here, right? So when we use the second or the L2 norm in the regularizer, this is called the L2 regularization, or it is called the rigid regression problem. Actually, this is the most frequently used regularization. So like this one. So here, lambda is the penalty parameter. Okay, lambda should be larger than 0, and W square is equal to summation of the Wi square over I. Okay, so this is the definition of the L2 regularization. The main effect of the large model weight. The main effect is that the large model weight Wi will be penalized or avoid, since we consider them unlikely. We don't want large model weight So we want to penalize those large model weight. So this is the role of the regularization. Okay, so yeah, this is the definition of the regularization, and actually there are several kinds of the regularization. The first of all, there is the L1 regularization. This is called the lasso. Comparing to this one, the shape of the regularization is the L1 norm. So for the L1 regularization, the optimal solution is likely going to be sparse compared to the case where we use the L2 regularization. If you want to know the deeper, please find the what does it mean. But in this course, I just mentioned I want to just introduce this one. So if you want to know if you want to understand much more, please find the other material in the website. Okay. And there are another kinds of the method to reduce the overfitting problem, something like the shrinkage, dropout, weight decay, or the early stopping of the optimization, something like that. So in this lecture, in the today's lecture, we can't talk, we will not talk about those kinds of things, but in the deep learning lecture, we will discuss those kinds of things. Okay, so people move on to the another concept. Okay, here is the regularized linear regression problem with the original linear regression function with some kinds of regularization term. So yeah, here is optimization. What if this lambda, what was the lambda? The penalty parameter, right? What if the penalty parameter is set to extremely large value? Let's say lambda is equal to 10 over 10, something like this. This is extremely large, right? Then what happened? What happened? Okay, let's see the example first. Okay. So if this term is extremely high, let's say if there are we have a mapping function, something like let's say x0 plus w1 x1 plus w2 x2, something like this, right? Let's say something like this. Then if this parameter is extremely high, the effect of this term will be eliminated, right? So in this case, the mapping function really looks like this. So this is the case of the underfitting problem. So in this case, fwx is just equal to no. It should be w1, right? So it's just the w1. Okay. So in this case, if we just use the extremely high values of the penalty parameter lambda, the mapping function will be the overfitted, right? So in this case, the algorithm results in the underfitting and the gradient descent will fail to converge. So we have to choose the proper number lambda to get the desired effect using the regularization